So, basics of the SN2. We have our substrate with our leaving group attached. We have our nucleophile. Since it has to form all at the same instant, the nucleophile comes in, attacks, forms the bond. The same instant we kick out the leaving group. I'm going to draw it slightly differently. We would end up with something like this. Okay, so again, our drawing is supposed to help us. That's the point of the mechanism. And we can use that to evaluate some of the details behind how and why this would work. Okay, so number one, notice where the nucleophile is coming in. Showing it coming in from the direct backside. Why the direct backside? Okay, if it went the other direction, it would run into the negative charge of the leaving group. Okay, that is our hand-wavy analysis. That's fantastic. It works, so we can accept it. The term that we can memorize to that now is backside attack. So in SN1, we're all concerned about the carbocation. In SN2, we're all concerned about backside attack. So we need to be considering things that would limit or prevent the ability for a backside attack. Okay? So the backside of that bond, there are some other bonds back there, right? Okay, so I want to minimize the amount of electron density that those things have. What would be the smallest amount of electron density I could put back there? Hydrogens. So if I made those hydrogens, what kind of carbon do I have? Okay, this would be our methyl carbon because there's no hydrogens connected or no carbons connected. Okay, so this would be a zero area. If I now switched it, where we now actually had that bond go out to a carbon, now it becomes primary. That has slightly more electron density, so it wouldn't react quite as fast, but it should still react. Okay, if we turned one of those other hydrogens into a carbon, we could move out to a secondary. Okay, we could move all the way out to the tertiary. The tertiary is not going to work for us. Okay. So we can use the mechanism to help us predict that information and consider what's going on with it. We can also use this mechanism to help us out with the background on a nucleophile. That nucleophile has to come into the backside of that bond. Right? Well, if there's a bunch of stuff there, that would repel the nucleophile. So what size should the nucleophile be? Small. As small as possible so it can avoid some of that steric interaction. So that now helps us to identify that our nucleophile will probably be smaller in this case. Okay. Do I want it to be charged? Yeah, it's trying to force the leaving group off. The only way I can force that leaving group off is if the leaving group takes all the electrons. So the more negative I can bring in, the more I can shift the electrons out the other direction. So a stronger nucleophile makes more sense. Okay. Solvent considerations. In the SN1, I wanted a polar protic so I could stabilize a carbocation. Do I have a carbocation? No. Okay. So I can't use the carbocation as the explanation for why I would choose my solvent. So now what I have to... You okay? So now what I have to do is consider that nucleophile, okay, and consider what would help it react. If I use a polar protic, that protic gives me an H+. What would that H+ do? React with the nucleophile, kills the nucleophile activity. No nucleophile activity? No reaction. So I don't want a protic solvent. A non-polar solvent means it doesn't dissolve. Okay? So I end up with polar aprotic. There's my solvent determination. Okay? So all of these things come out of evaluating that mechanism at its root core. Okay? And using all of the terms and concepts that we've been dealing with through the whole semester. Okay? So if we made it look prettier, we could see something like this. You'll notice just like we did for the E2, you can get a system showing the transition state or the transition state depending on, I don't know, what time of year it is. Yeah, there you go. Double dagger referencing our transition state. The nucleophile is coming in at the exact same instant the leaving group's leaving. The point that we're trying to show here is that that orientation of the nucleophile is now locked in to be directly opposite the leaving group. Which means if I started with a chiral molecule, I will likely end up with the inversion in stereochemistry. Okay? Likely. Why not guaranteed?
Are there any chance of rear ends that take place?
Nope.
It might not be chiral.
We're saying it starts chiral though. But you bring in an interesting point. What if the nucleophile that comes in matches one of the groups that's already there? Well, then it wouldn't be chiral anymore. Okay, so it would have lost chirality. Okay, the other kind of big consideration, the nucleophile has to have roughly the same priority as the leaving group. If the nucleophile comes in with a lower priority, RNS could potentially not invert. Okay? For the majority of situations, when you're looking at SN2, that is typically what is tested on. Right? You can see people trying to throw trick questions at you. Oh, here's an SN2 reaction. Do you get inversion? Right? And be like, oh, no, you don't. Well, you do. You always get that backside attack. But remember, RNS isn't dependent on the mechanism. It's dependent on the relative orientation of those higher priority groups. So we have to treat it as two separate questions and not as the same concept. Kind of makes sense? Okay. The other big thing to drop into this is the rate. Remember, your rate is dependent on the slow step. Since it's only one step, all of the reactants show up in that slow step. Okay? In this case, we get the nucleophile and the substrate. There's two things, so it's bimolecular. That's why it's SN2. Okay? So backside attack is our key word. You'll also hear reference to something known as steric hindrance. It's just a fancy way of saying electrons are in the way. Okay? SN1 we already broke down, so we could look at the pretty picture for it. If we evaluate this, you'll notice that I've added a step. Okay? Depending on the SN1 reaction, you might see a third step appear. Okay? A lot of that has to do with the nucleophile being used. Right? Because your nucleophile needs to be a weak nucleophile, it's typically not charged. Right? But by that same token, we can't make it a charged result. So one of the most common nucleophiles for an SN1 would be something like water. Okay? Problem with that is that if water comes in and attacks, the result that we get here would now be a charged atom. Does the atom want to be charged? No, so what happens? It has to shed that excess hydrogen through an acid-base step. Okay, so you might see that extra acid-base step in there depending on what the nucleophile is. Okay? When we initially start talking about our substitution reactions, we're only dealing with halides, in which case they're already kind of strong, but we just go through and say, well, do it SN1. Right? Well, then you don't have to worry about that secondary step. When we move out into kind of the broader circumstance of reagents, to get that weak nucleophile, we almost always have to have that hydrogen on there, and we have to be aware of that. Okay, so we could end up with a charged product that we'd have to neutralize before we got to the final one. Make sense? Okay. We've got our rate, okay, which then kind of takes us to our energetics. Okay, again, the whole concept of this is being able to look at an energy diagram and a reaction to kind of get a general feel for how your reaction is functioning. So if I asked you to go through and draw an energy diagram for the SN1 or the SN2, what might you draw? What are characteristics that you would expect to see?
I expect to see one hump for an SN2.
The SN2 is happening in one step, which means one hump. All we get is the transition state. In the SN1, 2 or 3 humps, minimally more than one, because we have heterolysis and the coordination. So we would expect to see at least 2 humps. Typically, in the case of our substitution reactions, they are slightly exothermic, so we would expect the products to be a little bit lower in energy than our reactants. Right? I know the slide just says SN1 and SN2, but we've already talked about the other ones, so let's take full advantage of that. What are the other mechanisms you're responsible for in this test? E1 and E2. What would we expect to see for the E1 and the E2?
I'd see the same thing. You'd see, except that I believe you'd see the same amount of
We'd see the same amount of humps because
same amount of
steps. Right? The question or the difference comes in, is the product going to be lower in energy?
No, it's going to be higher.
It should be higher in energy because
Because of the pi bond.
you're forming a pi bond, and the pi bonds are higher in energy. So if we look at an energy diagram for our eliminations, we might expect something more along these lines. Where they're now endothermic reactions. Okay? But the same general concept, same number of humps along the way. Make sense? Okay. That looks kind of like a test question if you ask me. Yeah. What are the repercussions of the different mechanisms? So when we run the SN1, what happens? So here we have a chiral molecule. The very first step in the SN1 is what happens? The leaving group leaves, the formation of the carbocation. If I have a carbocation, do I have a chiral atom anymore? No, I've actually lost the chiral atom. Okay? But I have a carbocation. In this case, I've taken the structure and I've turned it on its side. That carbocation is occupied in what kind of orbital? A p orbital. So there are now two lobes where we could place electrons. So that iodide nucleophile can come in and attack either from the top or from the bottom. Which means when we go through to try and look at our products, what happens?
You get a 50-50 split of cures cancer and instant death.
Yeah, I'm starting to regret saying it causes cancer and death and all that fun stuff.
But
It's kind of not very optimistic. Okay? We would get the result where the iodide came in from the exact same side the chloride was. That is a possibility. Okay? And we would also get the result where the iodide came in from the backside. Both of those come out as products. Okay? What I'm kind of chewing on is deciding how extreme that split is. Okay? If you have a chiral molecule present, that can mess with how the chemistry happens through the rest of the experiment. So what I would like you to remember is that these come out as 50% each. Is it true? No. Okay? And in fact, if we look at this experimentally, it doesn't come in as a 50% split. We get more of this one. Why do we get more of that one?
Because if you come from the top, the leaving group's electrons.
If you come from the top, the leaving group's in the way. Is the leaving group in the way in the SN1 mechanism?
No, because it happens at different times.
No, because they're in different times. But a lot of that comes to the rough probabilities of those things happening. If the leaving group has left or is starting to leave, there's a slightly higher population or a higher chance the nucleophile could attack from the backside of that having left because the chloride's in the way. Yes, David?
You also have to look at the steric interference from the other bits of the molecule.
Yes.
You gotta
Less so. Less so.
but still.
It's really just the leaving group that dictates it
Oh, okay.
because those are in perpendicular planes to that forming pi bond. Or not pi bond, the p orbital. Okay? So you will get some people going through and saying, well, that other one forms more. They're not wrong. Okay? The problem is that when I write more, what do you now interpret that to be? That's now the product. If we look at the percentages, how much more? Hardly anything. Okay? So I would rather you that you memorize that the SN1 gets you a 50-50 split and be close to right than memorizing you get more of the opposite one and be 55% wrong. Does that make sense? So when you think SN1, you should be thinking racemic mixture, you get two products, okay, in a 50-50 ratio. Okay? There is a subtle nuance there. I don't think that subtle nuance is that big of a deal. Okay? Kinda?
Yeah.
Okay. What happens with the SN2? Since this is now all in one step, the iodide has to come in from the backside of that leaving group bond, which means when I go through to show the product, which product do I get? Okay. The iodide now must be aimed away because the chloride was aimed at. So I can show the iodide, and there's the methyl group. Notice the methyl group was away and is now pushed forwards. Okay, well, why? A lot of that has to do with kind of the chemistry here. So if we're looking at it, there's our phenyl in the plane. There's the chloride, my index finger aimed at you, and there's the methyl. Where's the iodide coming in and attacking? From the back side. Okay? This is going to look a little weird. Kicking the chloride out. Okay? If we look at that system, those groups are all really close to each other. So what happens? My thumb, well, it kind of works. It gets pushed forwards. Okay? And what you're getting is an inversion. It's kind of the umbrella flip, if you will. Okay? And that's what the textbook shows in a nice picture, which we might see here in a second. Okay? But that's what's happening with the SN2. You're getting that inversion. One of the things that I do want you to be cautious of, does that mean the nucleophile will always be dashed? No. The only reason the nucleophile is dashed in this case is because the leaving group is wedged. The leaving group does not have to be wedged. It could be dashed. It could be a solid line. Just make sure that when the nucleophile attacks, it comes in from the backside. Make sense? Okay. Another thing to kind of watch out for when it comes to the SN2 in particular, the SN1 is less important because we get both those products. Is there another way that I could represent this molecule? Could I have drawn it that way? And now when we look at that, we'd say, well, the iodine, the nucleophile, is coming at me. Well, that can't possibly be correct because according to my SN2, it must be aimed away. Okay? Remember, you're responsible for acknowledging that those structures are the same. Okay? So the answer may not be written explicitly how you want it to be written. We could take the structure and flip it and make it look wrong. So be very careful when you select your answers with stereochemistry or when stereochemistry is involved to make sure there wasn't a rotation of a sigma bond, a flip of the structure, anything very subtle like that, because that can very instinctively make you ignore those answer choices. Okay? If it looks like the structure has changed in any way, shape, or form, you should not immediately eliminate it. Okay? At least pause and consider it. Make sense? Okay. So in our visualization on this, I just attempted to draw this, but if there's our carbocation, that has what hybridization? sp2, 3 groups of electrons, sp2. Okay? That structure, the p orbitals coming in and out of the plane, not easy to see. This is why we can take that flat structure and turn it on edge, so it's kind of coming in and out of the board. Okay. Carty decided to rotate it on a totally weird axis, in my opinion. Instead of going kind of flat, they decided to rotate the structure this way. Okay. Which is still fair, but we're just looking at the axis differently. Okay, so that's what he's showing here. Your p orbital is now sideways in this. Okay, so the iodide can come in and attack that carbocation from either the right or the left, resulting in the formation of two products. Make sense? Okay. So all we're trying to do is come up with different manipulations so that we can see those structural representations. That's it. Questions? Okay. Maybe.
Do you end up with anything strange as far as you've got a pure goal and it's now with no pi? Do you end up with the resonance stabilizing that and locking it in place, or can that sigma bond rotate the one off of the?
So that's an interesting question. If we take a look at this structure, we do have that. Yeah, we have this p orbital, right? Is there resonance nearby? In resonance, what do we move?
Electrons.
Electrons. Which electrons are we allowed to move in resonance? Lone pairs and pi bonds. Do we have any lone pairs?
No.
No. Do we have pi bonds?
Yes.
Yes. Those pi bonds could be used to resonate outwards, and this is where it's going to look a little ugly. You get what I'm trying to show?
Yeah. I was just wondering if that
Okay.
was stabilizing enough.
Will that cause some overlap to keep that pi bond locked in? Yeah. Yeah, it will. It will have an effect on that will help minimize the rotation about that sigma bond. Okay? Minimize being the operative word. Okay? In this case, are we going to see a difference in the results? No. No difference in the results. So we don't need to stress about that. Okay? There are cases where I would have to worry about that. Say if I was making a pi bond coming off of that. Because in that pi bond situation, which pi bond do I want? Would I want a cis pi bond or a trans pi bond?
That depends on the product or what I was trying to get at.
Not in the case of a carbocation. I want a trans pi bond because it's more stable. So once I form that carbocation, the carbocation is going to align to form the most stable carbocation possible. That's going to cause the electron groups to be as far away from each other as possible,
Okay, I thought you were talking about
which then means when we complete the elimination, we're going to get the trans product. Okay? So we do have to consider that when we look at what would happen if I could lock that position.
Okay.
That locking position would happen in an elimination, not in a substitution.
Gotcha. All right.
Okay? One of the big problems that pops up, carbocations. Okay? Which is most stable of our carbocations? The tertiary is more stable than the secondary, which is more stable than primary, more stable than zeroary. The zeroary and the primary are so unstable. If you have a mechanism where you are attempting to form a carbocation on one of those two positions, either zeroary or primary, you should stop. That mechanism was a bad idea. Okay? And you should try a different mechanism. What would your different mechanism be? SN2, not a rearrangement, because the rearrangement assumes I've made it. Once I've made it, then the rearrangement can happen. So I could do an SN2 or E2. Right? So if I can't form a primary or zeroary carbocation, but that's where I'm seeing my partial positive charge, I'm probably doing a 2-type mechanism, not a 1-type. Right? What happens if I form a secondary, but it's close to a tertiary? Now we get a rearrangement. And that could be a hydride shift, that could be a methyl shift, that could be a whole giant freaking ring shift. Okay? There's a multitude of potential options that could come out of that. We need to be aware of those situations. Okay? That means when you run an SN1 reaction, you need to be thinking about rearrangements. Okay? So when I say SN1, you say carbocation. And when we say carbocation, you should be saying rearrangement. Okay? By connecting those three pieces, When you see an SN1, you now know to go to a carbocation. You also now know that you have to be considering rearrangements. Okay? When does a rearrangement happen?
Or something more stable nearby?
If it generates a more stable structure. If that structure is not more stable, the rearrangement does not happen. Okay? So if we went through and looked at the situation we have down below, we're talking about the shiftable group. All right, let's take a look at what 1 and 2 are. Let's call 1 a methyl, and let's call 2 a methyl. Would this result in a more stable carbocation?
Yes.
Yeah, we're going from a secondary to a tertiary. So that is more stable. What if it was a hydrogen?
No, you're just going from the secondary to another secondary.
We're going from a secondary to a secondary. That's not more stable. There's no reason to do it. Okay? And while you might be okay with that, usually what happens, okay, let's see if I can just redraw all of that. Usually why students would go through and attempt something like that is that if we went through and had a structure like, let's see if I can pull this off. Yes, I think I can do it. Students would say, well, it would be more stable if I had the carbocation here. Would it be more stable if I put the carbocation there? I didn't ask if it's possible. I just said, is it more stable?
Yes.
Yes. This would be a tertiary versus a secondary. Okay? So your first statement, it's too far. When we do a rearrangement, it has to be close. Okay? So what students will still do is say, well, it's still more stable there. What happens is I took a hydride here, did the rearrangement, and I end with this structure, and then I do the rearrangement, and I end here. See, Mike, I made it. Okay? You're right. That last step, I completely agree, is 100% favorable. I'm going from a secondary to a tertiary. Completely agree with you. Could you make that secondary?
No,
No. Why not?
because it's not more stable.
It wasn't more stable than the first step. Okay? And this happens a lot of times. You'll go through and draw something that's horrible and be like, oh, I can make it better. Of course you can. It's horrible. Okay? Don't focus on what you can do to fix something. Make sure you're allowed to make it first. Okay? So that first step is now not possible. If the first step isn't possible, I don't care what happens after the fact because it's not allowed to happen. I can't get to that first step. Make sense? Okay. So, carbocation rearrangements with SN1. If we go through and run this mechanism, what mechanism are we doing? SN1. Thank you. And I like the little smile because you're saying it's SN1 because it says SN1. I love it. Try again.
We're doing a heterolysis.
That doesn't tell me it's SN1. You're saying it's SN1 because I'm going to make it a heterolysis. Well, the only reason I do a heterolysis is because it's SN1. Your logic is cyclic.
Oh, so I have to get
We have to look at the species that are present and use the species to dictate what our answer is going to be. The substrate is secondary. All mechanisms allow a secondary substrate. So the substrate as information is useless. So I would move to the next piece, the nucleophile. Strong or weak? Weak. A weak nucleophile does not work with SN2. So because I have that weak nucleophile, I now have a tip-off that I'm going to be going in the one-type mechanism screen. Okay? Now that I know I'm in the one-type mechanism because of that weak nucleophile, now I can initiate a heterolysis. That heterolysis gives me a carbocation. Okay, so I said weak nucleophile SN1, carbocation, rearrangement. Is this rearrangement an allowed rearrangement?
Yes.
I'm going from a secondary to a tertiary. That is a more stable situation. So that rearrangement is allowed. Okay. Now what do? Is that my final product?
No.
No, why not?
You need a charge.
It's charged. Okay, so it is not a final product. I need to stabilize that. What do I need to stabilize that positive with? Electrons. Where are their electrons? The oxygen with water. The oxygen can attack. And I think I started to hear some mumbling in the back because you probably started predicting that out. Is this now my final product?
No.
Because
Charge.
still charged. Are you suggesting I should stop giving you hints? Is that what that is? I'm gonna mock my ch-ch-ch. Now do I have a final product?
No. You didn't include the H3O or the I.
So, interesting statement there. I heard that we needed H3O plus and the I minus. Okay, so let's walk through that. I minus, does everybody agree that the I minus should be showing up? Okay, you understand where that came from? H3O plus. Where did that come from?
From the hydrogen that went off attached with the H2O that was left over.
Okay. Came from there. Water was the base that was removing that hydrogen. That's why it says 2 equivalents of water. Water showed up once as a nucleophile and a second time as a base. Okay, that's where H3O plus came from. Okay, so now back to the initial question. Why did I not write H3O plus and I minus?
Because you were trying to trick us.
Try and trick you. Hey, I do that a lot. No.
They're not our organic product.
What is this class?
Organic.
Organic chemistry. Do I care about the H3O plus and the I minus? No. Why not?
Inorganic.
They're inorganic. We can make they're still products. Yeah, you're right. Okay? And depending on what you want as your validity in this reaction, you may decide that you need to include those. You will find that most organic chemists don't show those pieces. Okay? Is it a horrible habit?
Yes.
Absolutely. Okay? Is it a habit that doesn't have an effect on an organic chemist? Yeah, so we usually don't care.
Does it?
Does it affect students? Yes, because as students, what do you look for? A balanced chemical reaction to help you figure out where those pieces went. Right? So since it looks like we're getting a lot of head shakes that you want it balanced, if you see an equation that I didn't balance, feel free to call me out on it, okay, so that we can see those extra pieces. Okay? But arguably, we don't need to show those. Yes?
Should we start getting ready for questions that don't include? So, like,
I can almost guarantee you, hands down, that those products will not be shown in a reaction.
So I get that, like, so what is actually written on the screen, or not what you wrote, but the initial text on the screen.
Let's see if I can pull this off. So, questions that could be asked. Don't worry, I'm not deleting it. Whoops.
I get a question whoops.
What's the product? That's the product. That's what you would be expected to bubble in. Okay? What is the mechanism for this reaction? That one runs into a little bit borderline. This is going to come into actual preferences from your grader, i.e. me. That's what I would expect. Okay? Do you find it useful to include those pieces? Yes, by all means, go ahead and include them. Okay? But those pieces tend to be ignored. And you will find that I also tend to ignore even this one. For those of you that missed that, that was the water that was removing the hydrogen. Okay? We're talking about a very quick and easy acid-base step. It's not one that's really driving any of the chemistry behind this, so it's not that important for me to show what base is removing the hydrogen. Is that a bad decision? Potentially. Okay? That could potentially be a fatal one for a mechanism. Okay? But under most circumstances, the protonation and deprotonation step, where those things are coming from, isn't a big deal as long as they aren't coming from nowhere. What do I mean by coming from nowhere? Would that be a good product?
No,
No, why not?
because now you've got a strong nucleophile.
Step away from the strong nucleophile.
Oh, look, you don't have oxygen.
I don't have friggin' oxygen. Don't show it coming in and doing something. Right? So look at the pieces that are present. For the most part, we focus on the organic structures. Okay? Make sense? Okay. SN2, the repercussions. Okay? This is where Carty has the nice little pictures, so I use his pictures for the most part. We get that backside attack. That backside attack means the iodide's coming in from the backside. If we visualize this, here's our umbrella. Okay? Notice in this case, the chlorine, the structure has been rotated so the chlorine's in the plane of the paper, which means the backside of the bond is still in the plane of the paper. Okay? Which means our iodide comes in solid, not as a wedge or a dash. But that solid is now aimed the opposite direction. Notice also what happens to the other groups. The wedge and the dash were aimed towards the left of the structure on our starting material, and they're now aimed, yes? You had it. They just shifted positions a little. They now moved to the right. Okay, and the biggest part of this is they shifted positions a little. Wedged, C6H5. Wedged, C6H5. I'm not switching all of those pieces. So when you run an SN2, it can be helpful to go through and align the leaving group in the plane that is easiest for you to manipulate. Okay? If it is easier for you to manipulate wedged and dashed for a reaction, then redraw the structure so that the leaving group is either wedged or dashed. If it is easier for you to show what happens to the geometry in the plane of the paper, then draw it in the plane of the paper. What's the question, Leslie? Or is that a snarky question? What if none of them are easy for you? That's a perfectly fair statement. And ultimately what that's getting back to, and this is why I think the SN2 becomes really hard, is gets back to chapter 5 and the manipulation of those three-dimensional structures. And if you had a hard time with that, these reactions are going to be hard for you because you're going back to a material that was hard for you and now you have to apply it forwards. And yes, that becomes difficult. So if none of them are easy for you, what should you do? You have to practice. You can cry a little bit too, that's fine. But you also need to put in that practice. Okay? That practice is going to help you find that one of those is better than the other. Much like when we drew chairs, when we draw out chairs, one of our chairs looked awful and one of them looked really good. Right? In this case, I'm saying there's two ways that you could orient your molecule. Find the one that works really well for you, use that one. Okay? If you have a hard time visualizing it, do we have an aid that could potentially help you with that visualization? You have the model kit. Have a model kit pre-assembled with that chiral atom and a little thing to be a leaving group, nucleophile, and say, how do I do this? Okay? That could help you with that spatial representation. Okay? Don't rely on the model kit, because that's going to take time. Okay? But you can definitely use that as an aid. Make sense? Okay. So E1. Okay, there's a crap ton of stuff on here, so let's take a minute and pull away some of this information. If we're going through and doing an E1 reaction, what's the first thing that happens? Okay, the leaving group is going to leave. So we've got a pretty complicated looking structure there. We have 2 chiral atoms associated with it, and that's where this becomes a big deal. Are you having a hard time seeing what's going on with that methyl, or just the structure in general?
The structure in general is pretty kind of thin.
I can make it a little bit bigger. We're going to run into problems with it being super big.
Yeah.
So those rings I'm going to turn into phenols. So pH. Which can make it a little bit easier to see. Everybody see that a little better? Okay. Your leaving group can leave. Okay. And now I'm going to do something I tell you never, never, ever, ever to do. I'm not going to redraw it. The leaving group leaves. And in leaving, what happens? You form a carbocation. This is where students tend to leave that other group as a wedge, and I would argue that is a bad idea. Okay? It's not that it's wrong per se. Okay? Why should that not be left as a wedge?
It's SP now. SP2.
SP2.
Why are you oscillating between SP and SP2?
Because there's a hydrogen.
Yes. There's an implied hydrogen hiding back there. Okay. With that implied hydrogen, does that help you lock that down?
Yeah, SP2.
It's now SP2. As SP2, what's the geometry? Trigonal planar, which means they're all in the same plane. You shouldn't be showing this with wedges and dashes. Okay? You should be showing this as a planar. I gotta keep using the right eraser. I should be showing this as a planar molecule. Yes, David.
Can you still, because I do kind of like the wedge and dash, but like.
And I'm actually going to bring in the wedge and the dash here in just a second.
As it is now, but wedge phenol and dash hydrogen?
Yes, that's actually the next thing I'm going to do. So in this representation, where's our carbocation?
It's that carbon.
Touche.
Where the plus is.
What orbital contains the carbocation?
P orbital.
Where's the p orbital?
Next to a phenol.
In three-dimensional space.
It's pointing out side to side.
Okay, in and out of the plane. That's where our carbocation is. That is very hard to see that. So what we're going to do is we're going to rotate this sigma bond. Okay? And the point of rotating this is not to say, well, now we're back to wedges and dashes, but it's to acknowledge, again, the geometry of why we're showing wedges and dashes. Okay? We're showing the wedges and dashes now to accent the fact, not so much of the wedge and the dash, but the presence of the carbocation. That's the point of doing that. Okay? This wedge and dash is drastically different than the wedge and dash of just deleting the bromine. Different meanings. Okay? And because it was a chiral molecule, I think I just effed it up.
Yeah.
God damn it.
The occlusion, or shit, I can't remember what that was.
You're using fancier words than I know, so no.
Newman projection.
We could use the Newman projection, yes. Okay, and
like this way better.
that's actually a decent viewpoint. We'll switch to that one in a second. Do I have a nice picture on that? Looks like I don't, but I actually have this hand or drawn out with pictures better than the textbook, in my opinion. So there's our alignment. Okay, what's the next step in our elimination?
You have to have something.
A base would come in, remove the hydrogen, and then the electrons can move into the pi bond. Okay? Is there an orbital here for the electrons to move into? Yes, so what can happen? Elimination can happen. Ta-da! There it is. It just happens. Okay? In that exact alignment. What do we end up with? So this was our H. I'm going to go H with an arrow, so H up. Okay? When we do the elimination, there's that hydrogen going back, there's this phenyl coming forward. What happened to the other carbon?
It's positively charged.
It's not positively charged. I took these electrons from that bond, and I moved them in to form the pi
So
bond.
it's still there, so it's the same.
It
Okay.
moves up.
What happens to the methyl and the phenyl?
Oh, they shift.
They shift from being angled downwards to now being in the plane. Do they turn? No. So where's the methyl? But remember with how our structure is oriented. I know why you want to go straight line because it's trigonal planar.
So it's going to be like sideways facing us.
The methyl is going to be coming out of the plane at you. Where's the phenyl?
And then the same as like the hydrogen.
Same as the hydrogen. And God, that looks ugly because what we could do is redraw that. Everybody see it?
Yep.
Okay. So what we're trying to show is how that elimination happened. Okay. Could I have just as easily, and here's where I need a little bit of help on this, am I okay to F with this initial structure, the carbocation?
No. Well,
I need to. That's what I'm asking. If you're okay with that drawing of the product from this drawing, I'm now asking permission. Can I delete this drawing?
Oh,
yeah.
Yes. Okay. In that deletion, I'm not going to delete the whole thing. I'm going to leave the carbocation half alone. This sigma bond can rotate. Okay? And it could rotate such that the hydrogen was now aimed down. Everybody agree? There's my carbocation. What would happen to the methyl and the phenyl? Okay? If I did that rotation, if we think about trying to grab that bond and now pull it out of the plane at us and rotate it down, that methyl was aimed at us down here. As I did that rotation, oh my gosh. Okay? Definitely rotated the wrong direction. Okay? It's now going to be aimed away from us, but now no longer below the plane, it's going to be above the plane. Whoops. There's my methyl. Where's the phenyl?
Out of the plane at us.
Out of the plane at us, again, up. Now when I go through and do the elimination, what's the end result?
Cis.
There's the phenyl, there's the hydrogen, there's the pi bond, there's the phenyl, there's that methyl, drawn horribly, but again, trigonal planar, so let's flatten that guy out. Everybody see it? What is the relationship to my purple and orange structures?
Trans versus cis.
Let's stick with just trans versus cis and E and Z. I don't think I'd call them, I think they're geometric isomers is the official label. Okay. They are cis versus trans. Well, which of those would we expect to form in the higher amount? We just drew a mechanism that said both of them were allowed. Why do you predict the trans to form, the phenyl or the purple, not the orange?
It's phenyl's big.
The phenols are so large that when we look at this structure here, we want those phenols. Didn't I say I was going to delete that? Yeah. Oh, well, I didn't.
No, you did. You just did it.
I just
down there.
redrew it instead of deleting it. Okay. Those phenols are going to orient as far away from each other as possible. Okay. So while that sigma bond can rotate, the phenols are actually displacing that rotation. Structurally, they're saying, don't rotate because I don't want to get near that guy. Okay? That slight favoring suggests that when we run the E1 elimination, I have the potential for two products, but I get a clear major. That clear major is going to end up being the trans. Okay? So in E1 mechanisms, I tend to see primarily the trans product. Okay? Primarily is a nasty word. We might be looking at 60-40. Okay? So it's definitely not 50-50. We can't call it a racemic mixture for multiple reasons. Okay? But it's definitely not that 50-50. But that difference between which one we get, trans versus cis, is really going to come down to how much that cis conformation is unstable. Make sense? Okay? So that's not quite what I wanted. So Carty has the version of this drawn in the textbook. Okay? I also went through and did it as well, except in my version, this is now the nice structures, except digitally done as opposed to by hand. So we walked through the exact same analysis, we just did it by hand as opposed to the pretty pictures. Make sense?
Yes.
Yes. There was a pseudo request for a Newman projection. Okay, so we'll take a look at that Newman projection real quickly.
I'm sorry, everybody. That's all right.
We're going to do it this way. Red will be in front. Blue will be in back. So if we look at this position, the hydrogen is going up. Okay, and so what we've done is we took that red atom and we pulled it out towards us. The methyl was coming out at you. In the process of that rotation, it's now on the right-hand side of the structure. The phenyl is on the left-hand side. If I go and look at the back atom, okay, I have the phenyl out here, and I have the hydrogen over here. Okay? And you might say, well, aren't those awfully close to these? That's exactly the issue. Okay? That those bonds get so close in that transition, in that carbocation state, that I don't want the phenols near each other. Okay? Remember, we also have the carbocation floating in the background. The hydrogen has to be on that axis to allow for the elimination to occur. I could rotate that back one to bring the phenyl over to this side, and that's where I end up getting this structure. That brings the phenols too close to each other. That is a sterically unstable situation. We're getting almost an eclipsing interaction of those phenyl groups, which isn't stable, so it's going to rotate back to favor this one. Okay? If this is my primary state, when the base comes in, the hydrogen's going to eliminate, and I'm going to end up with my final form of the pi bond where they are now trans. Kind of get it? Newman kind of helps, doesn't it? A little bit. You might just be accepting that. That's okay. Okay? Ultimately, we just kind of have to keep that into consideration when we do our E1s. We have that carbocation. We have to make sure we're locked into a place where that hydrogen is in the axis of the pi system so that we can get the elimination. That typically means when we run the elimination with an E1, we get a trans product, okay? If that choice is even available, okay? Since we're talking about stability, let's take another swing at this. This structure is a little bit different, okay? If I ran the elimination here, form the carbocation, and now I'm saying there's two products. Why are there two products? So there's a suggestion of E and Z. Totally legit. That was not what I thought the structure showed. We get three products. How do we get three products? You must be smoking something, Mike. No, we get three products. Okay, you might be saying, well, when you do that, you're eliminating a hydrogen up here, and it's just a question of this rotation that caused that, right? And that hydrogen is located at what position? The beta position, because it is one away from the alpha. Is that carbon one away from the alpha?
Yes.
Yeah? Isn't that also a beta position?
Yes.
Are there hydrogens at that beta position? Could I do the elimination there?
Yes.
There's your third product. Okay? And maybe why you're being like, well, that one doesn't form. Okay? Why would that one not form? So you weren't saying that. Okay? So that's problematic.
Why would it not form?
Okay, why would that pi bond not form in deference to the other two? Well, what's the difference? Okay, so the top two, you could tell me cis and trans. So this was cis, this was trans. How could I label this one? Well, that one's not cis or trans, so I can't use cis and trans. So I'm going to make the statement that calling it cis and trans is a cop-out for deciding stability.
Conjugation.
There's no conjugation, but I think I know where you're potentially going to it. Conjugation is typically in reference to resonance. There's no resonance.
Okay.
Okay? What you might be referencing instead is that pi bond has two carbons potentially interacting it, whereas in the bottom one it has just one. The bottom one has only one substitution on it. Okay, so we call it one sub. The top two have two substitutions. More substitution is more stable. Okay? The hand wavy argument that I used for that we already discussed, was what? What makes all of those structures reactive? The pi bond. For the pi bond to react, what must it do? Yes, break, but then do what? Form with something else. Those electrons must leave the structure. For them to leave the structure, what must they get by? Whatever's at those 4 points. There has to be something there. Minimally, what is that something? Hydrogen. What else could it be? Carbon, nitrogen, oxygen, chlorine, bromine, iodine, sulfur, silicon, phosphorus. I already put sulfur, didn't I? Okay? It could be a ton of different things. Why am I grouping all of those things and leaving hydrogen separate? Hydrogen is small. Why is hydrogen small? It has the least amount of electrons. For the electrons to leave the structure, they must get by something. Okay? It is easiest for them to get by hydrogen because it doesn't have any electrons. We'd get an electron-electron repulsion. So if I put something with more electrons there, can the electrons make it out that position? No, it becomes a little bit more difficult to go that way. So what happens? The electrons try the other route. I put something there. They try the other way. Put something there. Other way. Put something there. This structure, I've now blocked those corners. The electrons it's more difficult for the electrons to leave those positions. Because it is more difficult for the electrons to leave, they're now stuck. If they're stuck, they're more stable. They can't react. Okay? So when we look at pi bonds, we don't reference primary, secondary, tertiary. What we reference is the amount of substitution, and in particular, the amount of non-hydrogen substitution. The more substituted the pi bond, the more stable the result, and the more likely we form it. Okay? Does that make physical sense? Cool, that makes so much sense that we should just explain the chemistry behind it. And instead, what do? Zaitsev's rule. Why do we name it after somebody? That was pretty freaking logical. Okay? We named it after somebody because they made that discovery before they knew about the existence of electrons and protons. That's pretty insanely cool. Right? So that's why we're naming it after them. We're giving them credit for that, and that's kind of neat. Okay? Strictly what we're looking at is a Hammond postulate, argument, transition state, and all sorts of fun stuff like that. But this ends up getting called Zaitsev's rule. We could bring in an energy diagram that I don't feel like doing, but we could. We'll look at heat of hydration in a second. The more substituted double bond is the more stable. Okay? So 4 substitutions, or tetra substituted at the top, tri, di, and mono. Okay, we can get cis and trans things in there. But really what it comes down to is in your elimination reactions, if given a choice, you want to form the more substituted double bond. This is Zaitsev's rule. Okay? And so we memorize it. That's Zaitsev's rule. So when we do eliminations, that's what we expect. Or When we do an elimination, should we make the most stable product? Yes, I would argue that should be your focus, not looking at Zaitsev's rule. Okay? Are there exceptions? Yes. Now you should memorize an exception. Okay? Instead of memorizing Zaitsev, memorize I want the most stable double bond. There are exceptions to that. Those exceptions have to do with the structure of those individual pieces. If for whatever reason something prevents the formation of the more substituted double bond, that is now not following the rule. And that gets named Hoffman. I would argue you have a legitimate reason for naming that one because it's going against the logical rule. If things go against logic, we should give credit for the person that was like, actually, here's why your logic is dumb. That's pretty cool. We should give them credit for that. So in a Hoffman elimination, it only happens in an E2, and it's referencing a sterically hindered base and a sterically hindered hydrogen. Okay? So you have to have a sterically hindered base. Okay? Why? Well, let's go back to our diagram here. Oh my gosh. Okay? If we looked at these, C is our highest, followed by A, followed by B, right? For our products. In this case, we're going to do it as an E2. Everybody agree with that?
Yes.
Okay. Ignore the red thing at the bottom for the moment. So what's happening is we're going through, there's C. There's A. There's B. If we look at which product we're going to form, because it's an E2, it's all happening in one instant, I want to form the most stable double bond. Okay, the E1 is going to have a similar situation, but we're looking at the intermediate to the final product. Okay? I want that more stable double bond because the activation barrier is less. Okay? That activation barrier is less because I'm not considering anything of the sterics there. That's where things become tricky. What happens if the base I use is massive? So there's my little negative base, except it's really big. Can that negative base get in as easily to this hydrogen? No, now it's going to become more difficult for it to get there. Because it becomes more difficult for it to get there, there's a structural consideration. What happens to the energy diagram? That transition state for those two lower ones spikes. Now when we go through and look at the result, what happens? Okay. The least stable product becomes the favored one because its transition state is less affected by that steric effect. Because the hydrogen removed from that less one is right there at the back end, which is the most accessible. Okay? So what we're seeing is how the heights of those transition states can affect our overall reaction. That is insanely tricky to deal with, which is ultimately why I would push, in this case, memorization. If you have a sterically hindered base, do the opposite of what you would expect it to do. And you now have the correct answer. Kind of makes sense? Okay. We'll do a quick thing about heat of hydration. What does hydration mean to you? And actually, it shouldn't be heat of hydration. It should be heat of hydrogenation.
Attaching hydrogens to something.
We're adding H2. So we're going from a pi bond. Whoops. What structure am I drawing? There we go. And I'm going to ignore the middle one and this one. If I add H2 to both of these molecules, what would the structure look like? So I add H2 to the red one, what do I get? Butane. I just added two hydrogens to it, I get butane. What if I add two hydrogens to the purple one? I get butane. I get the exact same structure, so I'm ending at the exact same point. When we talk about the heat of hydrogenation, what we're talking about is how much heat is released when I go from my alkene to my alkane. That is my heat of hydrogenation. Which of these is going to have a smaller heat of hydrogenation? Purple. Sorry, I removed all the A's and B's. The purple one has the smaller heat of hydrogenation because
the difference is smaller.
the difference is smaller. Why is the difference smaller?
Lower energy.
That pi bond was more stable. It's lower in energy. So you can use, really when we're asking about the heat of hydrogenation, what we're asking is which of these double bonds is the most or least stable. That's all it's getting asked of you. Okay? But it's embedded in this hydrogenation thing, which then confuses people. Hydrogenation is just the addition of hydrogen, alkene to alkane. The alkane is effectively the same energy. The alkenes are all going to be different energy because different levels of energy of the pi bonds. So depending on where we start, we're going to change our heat of hydrogenation. Right? I believe there's a question in Smart Work about that. I honestly don't remember if I included a question on it on the test. Okay. It is kind of a favorite question of the ACS. Hydrogenation, the other one they'll ask is combustion. It's the exact same process. Right? They're really just saying, because combustion, what do you end with? Ouch.
CO2.
CO2 and water. Doesn't matter what we start with, we end with CO2 and water. Okay, so it's the same ending point, which is lower in energy. Okay, so all we're asking is what's the starting point? The more unstable your starting material is, the larger the heat in combustion. Okay? I did ask you to shift gears, so it's okay. Don't stress about that. I'm sort of judging.
I don't know.
I can't help it. The big thing I want you to remember is this Hoffman elimination as an exception. Okay, I know that's really tiny. It plays a relatively minor role, but it's one of those exceptions. And of course, what do we do with exceptions? Not only that we memorize them, but we also then test you on them. Okay? Do you understand when the chemistry doesn't hold true to its standard results? Okay? So, Zaitsev's rule, if we were to go through and look at this one, what would we expect for our product? Notice in this case, how many different products would we get? Okay, because I see lots of people thinking and not writing. We're going to point out a common mistake made on exams. You open up the exam, you look at the question, and be like, I think I can solve this without writing anything. No, you can't. When you read the question, start writing. So when I ask you how many products are there, what should you immediately be doing? Writing. You need to just accept that you have to draw. Okay? Draw. What are the products? An interesting observation was made. That structure looked weird. Yes, it did look weird. It looked weird because you saw hydrogens. And what do we do with hydrogens?
We don't show them.
We don't show them. Why did I show them?
Because those are the beta targets.
To help you lead towards seeing those beta positions, to help you focus on what those other possible products could be when you run the elimination. When you see a structure like this, you should immediately, if you think elimination, identify all of the beta positions and show hydrogens at those positions if they're there. Right? So that's one of the most common mistakes that happens with elimination reactions, is you only do the elimination with the hydrogen that you see. Well, if no hydrogens are there, you don't do an elimination, is the first option. The second option, you do the elimination with the first hydrogen you see. What if that hydrogen was wrong? you get the wrong answer. Okay? So when we do eliminations, you should be very careful to make sure that you see those hydrogens so that you can run those eliminations. Okay? So if we go back to the work that's shown with those hydrogens on there, we could have gone through and removed that hydrogen. The result, that pi bond. I could have gone through and I removed this hydrogen. The result, that pi bond. Or I could have removed,
You missed a methyl. Thank you.
or I could have removed, thank you, the bottom hydrogen. Now that I have three structures, now I can answer the question, which of those should have formed? If you don't go through and draw those, what ends up happening is you will draw maybe one of them, if you're lucky, maybe two in your head. You're going to get them confused and probably pick the wrong of those two anyway. That ignores the fact that there was a third one. As soon as you see it, you should immediately draw those structures. Okay? Focus on getting that information written down so that you can evaluate it. If you're doing it in your head, that's where you're running into problems. Okay? Yes, that takes time. Taking time to get the answer right is a good thing. Okay? Taking time to not get the answer at all is a bad thing. Okay? Write your work down. Okay? So in this case, which of the products is the most stable?
Blue.
I'll accept that. The blue one or the left one, because that one is more substituted. How many substitutions does it have?
4.
Okay, that would be our tetra substituted. What is the red one?
Dye substituted or bi-
Di substituted, the last one, not David. Tri substituted. A lot of people seem to have a problem nailing those down. That's why I asked. Yes, David.
As far as if you were doing this with a Hoffman's rule base.
If we switch this to now a Hoffman base, what happens? This one's going to become a lot more complicated, number one.
Because
Okay.
I was curious, because yellow would be the one, I mean, I would think that red would be, depending on the size of the base, red's the farthest out. as
And
far
that's typically where the Hoffman comes in. Is the Hoffman is this weird kind of borderline thing. They wouldn't ask it when you get three different cases. Typically the Hoffman is going to be between two choices, and you're going to push to the extreme. You're going to end up with the red.
Red, okay. So if
Okay.
you could only get blue or red, we go with red?
Yes.
Okay. But I mean, like, you could get to the point where the Hoffman base is so large. that
So
it's so red.
one of the problems that we're going to encounter with this one right away, is this going to be a good reaction to potentially run?
For Hoffman?
For anything?
Oh, no.
Probably not. Why?
You get 3 different products.
There's 3 different products. Okay? We may get varying amounts. There may be a major one, but there's still 2 other products that's going to detract from your total overall yield. Okay? So really this kind of question would be more of a, do you understand the nuances between which one you would get as major and minor? Okay? And that's where you would need to focus. It's not a synthetically useful one. And of course, this is a massive topic. So we'll have to end there.